predicting reaction rates and writing rate laws. Do you recognize this light stick? It's in ice water. Well, that same ice stick was put into hot water. It got brighter, right? So the reaction's happening faster. Tums. If you are the manufacturer of Tums, don't you want to know how long your product's going to last? You want to be able to control and be able to predict really well how much of it is left over time. And these sorts of things are really useful. And that's what we're going to work on today, is predicting just how fast reaction rates happen and writing equations for that. Whoop, I wanted to show you something here. Here's a reaction of A going to B. Now notice how we have all A at the beginning of this reaction. We have no B, okay? In order for the forward reaction to happen, I'm going to use this beaker. And for the reverse reaction, I'm going to use a smaller beaker. We're going to be talking about rate constants. So this might make sense later when we start talking about rate constants, but this is the rate constant for the forward reaction. It's huge. It's a very fast reaction. The reverse reaction, a much smaller rate constant. Okay? You're not going to get much going back in the other direction. Much smaller rate constant. Okay, so let's try this. So notice I'm not getting much at all as a reverse reaction. It's all going in the forward direction. When will I reach equilibrium? When the heights are the same? No. I'm going to reach equilibrium when I have the same amount in each beaker, going backwards and forwards. Because remember, equilibria is dynamic. So that means I have the same amount of product forming as I do reactant, right? Going in both directions. The amount of product and reactant, the concentration isn't changing over time. That's equilibrium. So I need to do this for a while before I can reach equilibrium. Let's see if I'm at equilibrium now. Right now I have about, what is that, about 30 milliliters. Here I have about, pretty close, right? About 30, little under 50, like 40 some. So I'm getting really close. And notice how the heights aren't the same. I have much more B than A. And the reason for that is this rate constant. So if I do this long enough, all right, then I could keep doing it forever, and the amounts of reactants and products don't change over time, and I'm at equilibrium, but the equilibrium is dynamic. So this is a great example of a dynamic equilibrium. Right around 30. Very close to 30. Okay. So there are some general ways to increase a reaction rate. See if you can circle your answers and get this. We could make the reaction proceed faster, right? Get product to be produced much more quickly if we increase the concentration of reactants. You can actually slow things down if you put in products. Increase the temperature, right? Things move around faster when it's hotter, especially when the reaction is endothermic, because heat is a reactant. We could allow these reactants to collide and strike each other much more easily by increasing their surface area. And we could use a catalyst. Okay, and more on that later, but it pretty much just reduces the energy hump that that reactants have to overcome in going from reactants to products. Okay, but we'll talk about that more later. Writing rate laws. What is a rate law? Well, the book reads, a rate law is an equation that relates the rate of a reaction to the concentrations of reactants raised to various powers. Okay. And what does that actually look like? If we have an overall reaction of this form, here's reactant A, reactant B, product C. Do you recognize little a, little b, and little c, what they were called? Do you remember? These are the numbers that you use to, to change, to balance the reaction. What was their technical name? Do you remember the jargon? Stoichiometric coefficients. Stoichiometric coefficients are the little letters. Those are just the numbers. Anyway, so if this is your general reaction, here's your general rate law. It's always the rate, and that's pretty much the rate that the product is being formed. It equals K. K is down here. K is just called a rate constant. And it's the same for that reaction. The only way to change it is to change the temperature. But if you don't change the temperature, K won't change on you. So that's why they call it a constant, a rate constant. And we're going to get it only after we know what X and Y are. So let's start back up at the top. How do you know what X and Y are? Well, you're going to have to do experiments. And the homework is going to give you a lot of experiments, and that's our job, is going to be able to pick the right experiments and determine what X and Y are. The homework might ask for an overall order for the reaction. All you do is add the exponents, X plus Y. That's the overall order. Figure out what X and Y are, add them up. If they ask for overall order, you know it. Do products ever show up in any rate law? Nope. It kind of does over here in the rate, but no. It's only reactants. These are only reactants. What do the brackets mean? Concentration. That's what the brackets mean. So the rate equals the rate constant K times the concentration of A raised to some X power times the concentration of B raised to some Y power. So if you increase the concentration of those reactants, you definitely increase the rate. Now, before we can play around with writing rate laws and figuring them out, we got to play with the math a little bit. See if you remember the rules of messing with exponents. This first one, A. What's X? 2 raised to some power is 4. Well, 2 times 2 is 4. Well, that means X has to be 2, right? How about 2 raised to the X power equals 2? X has to be 1. 3 multiplied by itself, how many times will give you 27? Well, 3 times 3 is 9, times 3 is 27, so that's 3 times. So X would be 3. How about this last one? You raise anything to the X, and you always get 1. X is what? Every single time. X has to be 0. Anything raised to the 0 power is always 1. Okay. So let's see if we can generally... Let's see if we can... Okay, now let's see if we can see how to generally approach these problems. Here's our overall reaction. Let's write a general expression for the rate law. So it always looks like this. You write rate equals K, and then you write in brackets the reactants. So you'd have E, and you'd have F. The concentration of E and the concentration of F, because those are my reactants. And then you have to raise them to X and Y. Not to the stoichiometric coefficients, just raise them to X and Y. Given a table of experimental data, find the order of each reactant. So, like the order of reactant E is X. The order of reactant F is Y. So they're trying to say, hey, find X and Y. That's what they want you to find. Okay, so we'll fill in this data table, but let's take a look at the game plan first. The game plan. Compare 2 experiments where the concentration of one of the reactants remains constant. Divide the values of the 2 experiments Substitute these ratios into the rate law, then solve for the order of the reactant that changed. Okay, one of three things always happens. Okay, so it looks confusing, but it's really not that bad. Okay, E is kept constant, F doubles, the rate doubles. So first let's write some data that would make sense for this. E is kept constant. Okay, let's say E is 5 in experiment 1. Well, then it's got to stay as 5 in experiment 2 because the E is kept constant. F doubles, so pick a number for F. Let's say it goes from 12 to 20, has to double, 24, right? Okay, so there's some data that makes sense here, that matches this. It says the rate has to double. Okay, well, the rate goes from 0.1 to, has to double, 0.2. I'm just making up numbers. That makes sense with this. Okay, now what we do is we divide, right? Divide the values of the two experiments and substitute these ratios into the rate law. Okay, so the rate law, just to remind you, rate equals K E to the X, F to the Y. Okay, so divide the values of the two experiments and substitute these ratios into the rate law. So let's divide the two rates. Okay, divide one rate by the other rate. It's always easier to divide the bigger by the smaller. So I'm going to divide experiment 2, right? Divided it by experiment 1. Then I get whole numbers, right? It'll be a lot easier. So the rate is first. So 0.2 divided by 0.1, right, is just 2. It doubled. Okay, we should have picked easier numbers, but that's okay. Right? Divide the two rates, you get 2. Divide the two Ks. Well, the rate constant never changes, right? They're not changing the temperature, so K over K is just 1. Okay, now let's divide the two concentrations of E. 5 divided by 5 is just 1 again. But don't forget to raise it to that X power. That's what that rate law is saying. Okay, now divide the two concentrations of F. 24 divided by 12, I get 2. Again, don't forget to raise it to that order, Y. So now we can figure out what one of these orders are. If you look at the math, you have 2 equals, well, 1 to the X is just 1, right? Because 1 to any power is just going to be 1. So that's all 1. You really just get 2 equals 2 to the Y. So that means Y has to be what? 1. So that's the first possibility of how this stuff is going to look. Let's try it again. Let's say E is kept constant, so that data is good. F doubles, okay, so that data is good. But the rate quadruples, so let's make something a little bit easier. Let's say it's 2, okay? Quadruples means multiplied by 4, right? 8. So the rate quadrupled, right? If it doubled, you multiply it by 2. Quadrupled, multiply it by 4. Okay, the rate quadruples. Okay, now we do the same thing. Divide the data and see if, find the ratios, substitute it into the rate law, and see what we get. Divide the two rates. 8 divided by 2 is 4. Okay. Divide the two rate constants, we get 1 again. Right, so I'm just following this. I divided the two rates. Now I divided the two rate constants for each experiment. Now I have to divide the concentration of E of each experiment. Well, 5 divided by 5 is 1 again, raised to the X power. Okay. Now I divide the concentration of F in each experiment. 24 divided by 12 is 2. Have to raise it to the y, though. Okay, so now my equation looks like this. I get 4 equals 2 to the y. So that means y has to be, what? 2. Okay, that's the second possibility of what's going to happen. One more here. Okay, they're saying E is kept constant. F doubles. So that data is all good. But the rate remains the same. Okay, so this has to be reduced to a 2. Okay, E is kept constant. F doubles. The rate remains the same. Okay, let's substitute it into our rate law. Okay, again, let's write our rate law. That might help you out. Rate equals K E to the X F to the Y. So we divide the two rates, and we get 1. Divide the two rate constants for each experiment. Well, we get 1, right? Divide the concentration of E. Well, it didn't change, right, for each experiment. So 5 over 5 is 1, raised to the X. Divide the two concentrations of F. 24 over 12 is 2, raised to the Y. So we have an equation of 1 equals 2 to the Y. So Y has to be 0. Okay. Okay. Let's try a few of these problems. Oxalic acid is oxidized by permanganate ion to carbon dioxide and water. So they give us the reaction. And then they tell us the rate law. What is the order with respect to each reactant? Okay. This is almost a trick question because all you do, they told us the rate law. There's nothing for us to figure out. We just look at these numbers. What are these numbers here? For permanganate, order is, what's that number right here? It's a 1. Right? The oxalic acid order is, it's not a 2, it's not a 3, it's not a 0, it's a 1. Right? We never write them. Right? We're always too lazy. Even the book is too lazy to write superscriptive 1 there. And the overall order, remember how to do that? We just did what? Add up the exponents. 1 plus 1, 2. Okay. Okay, this is going to be more of a typical homework question right here. Chlorine dioxide is a reddish yellowish gas soluble in water. Okay, they give us the reaction. To obtain the rate law for this reaction, the following experiments were run. And for each, the initial rate of reaction of chlorine dioxide is determined. Okay, so here's a bunch of rates, and they give us the concentration of the reactants, right? Chlorine dioxide and hydroxide. There they are, chlorine dioxide and hydroxide. Okay, so remember the game plan. We picked 2 experiments where the concentration of one of these reactants did not change. Okay, to see some to pick out. Let's pick experiments. What? If we picked experiments, oh, let's do 1 and 2. Because look at hydroxide didn't change. Let's pick experiments 1 and 2. Now, which one do you want to divide which one by which one? Divide the bigger by the smaller, right? So let's experiment 1 divided by experiment 2. Okay? So divide the two rates. Right? If you're not sure, you could, I think it helps to write the general rate law, because then you know kind of what you're going after. We should do that. Rate equals K, reactants in brackets, and then don't forget to raise them to this x and y. So here's our general rate law. This is what we're going to try to find. Okay, it's kind of nice because then we know what ratios to find. So first we find the ratio of the rates. So we need 0.0248 divided by 0.00276. Divide those two rates, and I got about 8.98, or 9. Okay. Divide the two rate constants, I get 1. Divide the constants, all right? Now divide the concentration of chlorine dioxide. Okay. 0.06 divided by 0.02, that's 3 raised to the x. Right? And now the concentration of hydroxide, its ratio raised to the y. Hydroxide is 0.03, 0.03, that's 1 raised to the y. So what's my equation going to look like? It's going to be 9 equals 3 to the x, but 1 to the y is just 1 again. So I'm ready. X has to be 2. So I'm halfway there. My x has to be 2. Okay. See if we can find 2 other experiments now. Let's pick what experiment divided by what experiment. Do you see it? Let's pick experiment 2 and 3, because look, the chlorine dioxide didn't change then. And let's divide experiment which one by which one? Divide experiment 3 by experiment 2. Right? Because 3 has bigger numbers. So again, we follow our general rate law here. Let's divide the two rates. So we'll have 0.00828 divided by 0.00276. You get about 3. Divide the two rate constants. I get 1, because that never changes unless you change temperature. You don't have to worry about that. The two chlorine dioxide concentrations. Well, I'll just get 1, but don't forget to raise it to the x. Hydroxide concentrations. 0.09 divided by 0.03 is 3, and raise it to the y. So I'm ready to solve for my equation here. I'll have 3 equals 3 to the y. So that means y has to be 1. Okay? So I'm really close to finishing this, except they say obtain the rate law. So that's this. But I need a value of the rate constant to do this. Okay? So right now, my rate law equation looks like this. Rate equals K, concentration of chlorine dioxide, raised to the x, and we said x is 2, concentration of hydroxide, raised to the 1. I have to find K, and then I'm done. So all you do, remember, K never changes. So in all these experiments, they all have the same K. So that means pick any experiment and substitute that data into the rate law to get K. Pick any experiment and substitute into the rate law and solve for K. Okay, that's the game plan. But this only works if you find x and y first, right? Okay, let's just pick experiment 1 and be done with it. So the rate is 0.0248, has to equal K. Concentration of chlorine dioxide in experiment 1, I'm doing experiment 1 here. I'm doing experiment 1 data. 0.0248 equals K times the concentration of chlorine dioxide raised to the 2 power. So that's 0.06 squared. Hydroxide raised to the 1 power, 0.03. So find K. So I'll have 0.0248 divided by 0.06 squared divided by 0.03, about 230. Okay. So now I can finally write my final answer. Right? My final answer. The complete rate law in all its glory. Rate equals K, which is 230, concentration of chlorine dioxide raised to the second, hydroxide raised to the 1. And you can write a 1 there or just leave it blank. There's my answer. Okay. So let's do the same thing, but now we have a different reaction, a different set of data. So we want to get the complete rate law. So that means even getting what K is. Okay. I think it's best to write that general rate law first, so it kind of gives you a hint what you're doing. Rate is going to be K, each reactant in brackets, raised to these powers. So there's my general rate law. Okay. Now we can go ahead and get started. Let's pick a couple experiments. I'm going to pick, let's see, let's do 1 and 2 again, right? And which one is bigger? It looks like experiment 2 is bigger, has bigger numbers. So I'm going to divide experiment 2 by experiment 1 and find out what those ratios are. So first, divide the two rates. I'll have 8.25 times 10 to the negative 3 divided by 2.75 times 10 to the negative 3. I get 3. Divide the two rate constants. I get 1. Concentration of NO raised to the x, 3.6 times 10 to the negative 4 divided by 1.2 times 10 to the negative 4. You get 3 raised to the x. Chlorine, concentration of chlorine raised to the y. So you divide chlorine's concentrations, it didn't change. So you just get 1 raised to the y. So our equation ends up being 3 equals 3 to the x. Everything else is just 1. So my x is going to be 1. Okay. Let's see if we can find another couple experiments. Let's pick what experiment divided by what experiment. Let's try, it's like 1 and 3, right? Because now you want the other one not to change. 1 and 3. And it looks like experiment 3 has, right? Experiment 3 has bigger numbers. So experiment 3 and experiment 1, but we need to divide experiment 3 by experiment 1's data. So let's start again. Divide the two rates. I have 1.15 times 10 to the negative 2 divided by 2.75 times 10 to the negative 3. You get about 4.18. It's pretty much 4. So you can write 4.18 or just write 4. Either way, it'll work. Okay. My rate constant, K, divide the two Ks, I get 1. The concentration of NO, its ratio, well, that didn't change. So it'll be 1 raised to the x. Concentration of chlorine, well, it went from 9.6, 10 to the negative 5, Divide that by 4.8 times 10 to the negative 5. Get 2. That has to be raised to the y. So my equation ends up being 4 equals 2 to the y. Everything else is 1. So what's my y? It's got to be 2. One last thing, find the rate constant. Not quite done. So pick any experiment, substitute it into the rate law, and we'll have our answer. Let's find k. I'm just going to use experiment 1 data again. It really doesn't matter, right? Any one of those experiments is going to give you the exact same k. Okay, so my rate, experiment 1 data, 2.75 times 10 to the negative 3 has to equal the rate constant, right? I'm just copying this guy. The rate first has to equal the rate constant times the concentration of NO. In experiment 1, NO is 1.2 times 10 to the negative 4. Has to be raised to the x, and I found my x to be 1, times the concentration of chlorine raised to the y. Chlorine in experiment 1 is 4.8 times 10 to the negative 5. It has to be raised to the y, and I found y to be 2. Okay, so let's take 2.75 times 10 to the negative 3. Let's divide it by 1.2 times 10 to the negative 4. And let's divide that by 4.8 times 10 to the negative 5. You got to square it. Where's that button? And I get about, oh my goodness, a big number. What do I get for my k? I get 9.9 times 10 to the 2, 4, 6, 8, 9. Huge number. Okay, so we can write our final answer then. Rate equals 9.9 times 10 to the 9th times the concentration of NO raised to the 1, right? And then chlorine raised to the y. And we said y was 2. There's our final answer. Okay. So the general idea in doing these problems, it's not so bad. You're going to be given a bunch of data. Write the general rate law. It'll help you out, right? And then you pick 2 experiments where one of the concentrations didn't change, substitute their ratios, dividing the bigger data into the smaller data, right? Dividing the bigger data by the smaller data, right? So you get nice whole numbers, and you'll figure out one of those exponents. And then do the same for the other 2 set of experiments where something didn't change. Last step, pick an experiment where you just substitute into your rate law and you can solve for k.